Hello class, today I'm going to show you how we can analyze vibration of a part. It's not going to be complicated or advanced analysis. It's going to include just natural frequencies and harmonic response of the equipment and general analysis when we have vibration. If you needed more advanced material, you should go back to library and look for more details. Okay, so if you had a model with some vibrations like aerodynamic equipments, like a drone, anything with some continuous vibration, which we can consider sinusoidal forces applying to your part, you may be able to use harmonic analysis for that vibration. Okay, we can start with static structure analysis and draw a geometry. So that geometry can be anything. For now, I'm going to make it very simple, but you can make any complicated geometry you need. So for this case, it's going to be a small bracket with some load, and that load is going to have a sinus shape variation, so we can analyze that case. So let's draw our geometry. So just random. Okay. Okay. Hundred. Mm. 20. Okay. So it was 80, so 15, it's going to be 95. I made a mistake. So it's going to be 95 and 100. This one was 120 minus 30 is going to be 90. So done. To avoid any stress singularity, let's write this shape. Okay, let's fillet some stuff, some corners. Let me pull it. Maybe 60 millimeter. Now I'm going to add fillet, 30, 30, 30, 30. Basically, I'm making the geometry really simple and avoiding all the possibilities for the troubles. So let's put some $15. Probably it's not symmetrical, but yeah. Create holes for the support. Done. This is my bracket. So let's do the analysis, just general analysis for the bracket, apply the load and fix support, and see what type of deformation we are going to have for this simple bracket. Then we're going to identify the natural frequencies and modes. Okay, it's loaded. Sorry for the delay. Unit is millimeter. It's okay. For the mesh, I'm just making everything simple for myself, and maybe 8. Let's see if it's too rough. We may. It's yeah. For this, just presenting the result would be enough, but of course, it's not good to get accurate results. Where is the fixed support? I'm going to add fixed support here and here, and I need to add some type of pressure at the top. Maybe 1 megapascal, so it's downward. So with this arrangement, with this boundary conditions, I expect to have deformation in x-axis, the main one which I'm interested, and any vibration in x direction is going to be the one I'm interested. We may have some natural frequencies in other directions, twisting ones, the other forms or modes, they are present, but I'm not going to focus on those. So let's check, for example, total deformation and stress and solve it. Okay, so 0.01 millimeter deformation. It's very small, and it's just 1 megapascal pressure at the top, and you can see the maximum is in this top side because we apply the pressure, and these are the fixed supports, so we have the minimum deformation, and the top part is going to have the highest displacement or deformation there. Okay, we don't care about that. This is the stress. So remember this deformation 0.01 millimeter. Now let's continue with the analysis and find natural frequencies for this object. So I need to drag the model, but because the geometry is going to be same, I'm going to drag up to this model. So they're all connected, and I don't need to do redraw or anything, so they are there. So because I connected the model one, the new options is going to be available inside the model. So I'm again opening the model. Okay, now you can see for the static structural, which we did, everything is here, and now we have modal analysis options available here. So for the modal analysis, the only thing I need is that fixed support, and I don't need to have a load because it's I'm looking just for natural frequencies. So select the fixed support, drag it to modal analysis. Now I have that fixed support. I copied it here, and yeah, that's it. Now let's solve it. So Ansys is going to solve this modal analysis for this geometry and find all the natural frequencies and their corresponding modes, which is very important for us. Okay, let's see the solution. We have 6 natural frequencies starting with 600 to 3000 hertz, and let's this is just natural frequencies. We don't have the modes here. We don't know, for example, this 600 hertz, what type of frequency is that? Is it going to be like a horizontal one, vertical one, twisted one? Which one is it? So that is why I selected all of them, and I'm asking to create the mode shaped results. Otherwise, it's just natural frequencies. I need to know the shape. Now I have all the information. Let's Ansys to solve them. The first one is for 600, which you can read here, 663, the first natural frequency. Check out the maximum deformation, 31 millimeter. For the static analysis was 0.01. So as you can see, when we reach this natural frequency, we are going to have a huge deformation there. And what type? It is going to be like a side to side. The second one, 26 millimeter, left to right. Okay. Third one. Okay, top, the vertical one. Twisting one. Again, twisting in XZ direction. Twisting in YZ direction. Okay, but we know what type of pressure we applied to this geometry. We applied a vertical pressure at the top, so number 3 is going to be our frequency we are interested. This one, it's vertically applied, and when I apply sinusoidal pressure at the top, we are going to have this type of vibration, and the natural frequency is going to be this one, the third one, which is going to be important, and we need to avoid. So number 3 is 1696. So we need to avoid this. Now let's apply the force and pressure and see if we have the frequencies, what type of frequencies we have. So I'm going to close this and add harmonic response. Where is harmonic response? Here. Again, everything is going to be same, model, geometry, those stuff. And by adding this harmonic response, again, the new option is going to be available for our model. So up to now, I know the static structure analysis, what type of deformation I have, 0.01 millimeter. Here, I know if we don't have any vibration, this is the maximum deformation I could have. If I had vibration, the worst scenario and the worst case, which is the natural frequency, I'm going to have 24 millimeter deformation, which is very bad and we should avoid it. Now I'm going to investigate harmonic response. Basically apply the pressure, make it change like a sinus variation, and see what is the frequency for those for this arrangement. So again, I need to have fixed support. So let's drag it here, and I need to have pressure. So pressure also will be dragged to a harmonic response. Okay, now I have my setting for the harmonic response. I have fixed support and pressure. This load is going to change like a sinus graph. Increases, going to 0, negative, increases, like that. And the fixed support is there. 9, I need to identify what is the frequency I'm looking to investigate. So from the nodal analysis, I found that the third natural frequency is the one I'm looking, and it's important for me. So it's 1696. So I'm going to have a range which includes this one. So maybe 1500 to 1800. Okay, so let's go here. 1550, 1800 frequency. Let me hertz. 1500 to 1800. Okay, so it's in the range. And what is the intervals? I don't want have so many data. Let's go with 50. But if you want to get more result, a more accurate result, so this frequency is going to be smaller. So I'm selecting just 50. If you needed other setting, check these other settings. For example, you can add damping coefficient, and depends on the arrangement you have. Yeah, let's solve it. Okay, now I have the harmonic response solved. So let's insert the frequency response for deformation, because we want to see what is happening in for this object. Which direction? X direction. So this is X direction, which is the area we interested, and the frequency, the natural frequency was happening between these two rates frequencies. What was the value? It was 1696, which is between these two values, so we can get some results and see what type of deformation we have. Let's solve it. Okay, now we have very clear data. We can see our amplitude or deformation reaches the max around 14.5 millimeter for under 1700. So 14 here. So this frequency 1696, or around this, is the frequency we should avoid, and so go back to your design and change it and try to avoid this frequency or the condition of your design. Okay, so what we did for this video, we did static structure analysis without vibration. We consider no vibration present here, and we found very small deformation of this much millimeter. So if there was no vibration, this is very small deformation, and you check the material. If this stress is under yield stress, it's done. Of course, depends on the condition. You may consider fatigue analysis too. Then we did modal analysis to find out our natural frequencies. These are all the natural frequencies, and then their modes. We found all the modes here because the shape of the those natural frequencies are very important, and we found that number 3 is the one we are going to have because it's vertical in x direction, and our forces or the pressure is in x direction, so it should be in this this frequency as our major natural frequency. Then we did harmonic response analysis. We included all the support, fixed support, and load, and for the range of frequency we were interested, we did the frequency analysis, and we found that the exact frequency which we are going to have the maximum deformation. Now we know that we should avoid that frequency, and in our analysis, if you had like an electrical motor or anything creating this frequency, you should avoid it or change your part to not to get close to this frequency. Okay, thank you very much. See you next